today's Explainer, we are diving deep into the microscopic world of chemistry. Have you ever stopped and wondered why water is always exactly H2O? Or how atoms actually join together to form, well, literally everything we interact with every single day? The secret to all of this lies in understanding the fundamental grammar of chemistry. By the end of this comprehensive explainer, you are going to master how to decode chemical formulas, understand how atoms interact to reach stability, and learn the exact rules for writing and naming chemical compounds. So let's get started and decode this invisible world together. Now, chemistry builds sequentially, kind of like learning a brand new language. So this is going to be our step-by-step syllabus for today. First, we'll cover chemical formulas, which are basically the letters and words of our new language. Second, we'll meet the ions, the cations and anions that act as the dynamic characters in our chemical story. Third, we'll look at the nomenclature flowchart, which is literally a map for naming everything. And finally, step 4 will bring it all together, showing us how to write and name actual ionic compounds.
All right, section 1, chemical formulas, the language of chemistry. Let's jump right in.
So first things first, let's define our terms. A chemical formula is exactly like a recipe. It tells us the precise number of each kind of atom inside a chemical compound. It essentially lists out the elemental ingredients and exactly how many of each you need. When you look at a formula, those letters you see are just the chemical symbols straight from the periodic table. But here is the absolute most crucial rule to remember for our chemical grammar. If you don't see a small number, which we call a subscript, written next to an atom, you just assume that subscript is a 1. It's an invisible 1. It's just like in standard math algebra. Getting comfortable with this basic shorthand is your very first major step in mastering chemistry.
Okay, let's break down a couple of real-world examples to see how this works. First up, look at octane. That's the main component of the gasoline you put in your car. Its formula is C8H18. The C stands for carbon, and that little 8 tells us there are exactly 8 carbon atoms. The H is hydrogen, and the 18 means there are 18 hydrogen atoms packed into just one single molecule of octane. Pretty cool, right? But chemistry can get a little bit more complex. Look below that at aluminum sulfate. Al2SO4 Notice those parentheses? They surround the SO4, which is a polyatomic ion. That's basically just a group of atoms acting together as a single unit. That subscript 3 outside the parentheses means we have 3 entire groups of that SO4 ion. It's actually a brilliant little shortcut to keep chemical formulas neat and organized without having to write out a massive, confusing string of letters.
Let's practice reading some of this chemical punctuation because it really is like a math puzzle. Take a look at calcium hydroxide, written as CaOH2. Let's count the atoms. There's no number next to the calcium, so boom, we have 1 calcium atom. The OH is grouped in parentheses with a 2 on the outside. That 2 distributes to everything inside, meaning we end up with 2 oxygen atoms and 2 hydrogen atoms. Simple enough, right? Now look down at iron 3 chromate, Fe2CrO43. We've got 2 irons. That 3 outside the parentheses multiplies everything on the inside, giving us 3 chromiums. And since oxygen already has a 4 inside, we multiply 4 by 3. That gives us a grand total of 12 oxygens. You really want to master this atom-counting mathematical grammar before we move on to the next step.
Which brings us to section 2, ions, cations, and anions. Now that we can read the alphabet, it's time to meet the true characters of our story. You see, atoms are basically locked in this constant, invisible battle to achieve perfect stability. And in chemistry, perfect stability usually means having exactly 8 valence electrons in their outermost shell. In this war of the atoms that only have 1, 2, or 3 valence electrons find it way easier to just give away or lose those few outer electrons. Now, think about it. When a neutral atom loses a negative electron, it naturally becomes positively charged. We call these positively charged ions cations. And hey, if you ever struggle to remember that on a test, just look at the smart feline chemist we have here. Cations are positive. I know, it sounds super silly, but honestly, it totally works when you're staring down a blank exam paper.
But what about the other side of the battlefield? That's where we find the anions. Anions are completely different. They form from atoms that already have 5, 6, or 7 valence electrons. They are so incredibly close to that magic number of 8, what we call the octet rule, that it takes way less energy for them to simply steal or gain a few extra electrons to fill up their outer shell. And since electrons carry a negative charge, gaining them turns the atom into a negatively charged ion. So just to recap, cations are positive because they lose electrons, and anions are negative because they gain them. Let's look at exactly how that transformation happens. On the left here, we've got a perfectly neutral fluorine atom. It has 7 electrons in its outer shell.
It's just one tiny electron shy of a perfect octet. So what does it do? To form the ion, it pulls in one extra electron, which you can see on the right. Notice how that single added red dot perfectly completes the circle of 8? Because it took on one extra negative charge, it transforms from a fluorine atom into a fluoride ion with a -1 charge. And now it is perfectly, happily stable. Now, when these ions form from just a single atom, we call them monoatomic ions. And here is where the periodic table becomes your absolute best friend. It's basically a giant cheat sheet. Elements in group 1 always form a +1 charge, group 2 forms +2, and group 13 forms +3. Over on the other side, group 17 halogens form a -1 charge, group 16 forms -2, and so on. Now, let's take a really quick, fascinating detour. Notice how some elements in the middle, like carbon and silicon, don't readily form these ions? That's because instead of fighting to steal or lose 4 whole electrons, they prefer to form covalent bonds. In a covalent bond, nonmetal atoms actually share their valence electrons to achieve stability. Think of it as roommates sharing a TV because neither can afford one alone. It's all about teamwork rather than a tug of war. But for our ionic compounds today, we're going to stay focused on the strict givers and takers.
All right, moving to section 3, the chemical nomenclature flowchart. We know who our positive and negative characters are, so let's look at the official map for how chemists worldwide actually name them.
This flowchart is an absolute lifesaver. It acts as our personal tour guide through the sometimes overwhelming world of chemical naming. Right at the top, compounds instantly branch into 3 main categories: ionic, molecular, and acids, and depending on which path you take, the rules change entirely. For example, molecular compounds use a prefix system, which is why we say carbon dioxide. But ionic compounds, which is our focus today, drop down into binary compounds and polyatomic ions. They rely on simple main group elements or the stock system for transition metals. We absolutely do not use prefixes for ionic compounds. Seriously, having a mental map of this flowchart will save you from mixing up the rules.
Finally, we've reached section 4, writing and naming ionic compounds. Let's see how all of this builds into practical application. We are going to learn how to write binary ionic compounds. Those are compounds made of exactly 2 different elements. To do this, you just need to master the 3-step crisscross method. Step 1, write out the symbols for the ions and their charges. And always write the positive cation first. Step 2, cross over the charges. You take the absolute value of each ion's charge number and pull it diagonally down so it becomes the subscript for the other ion. Step 3, simplify those subscript numbers if you can, and tying it back to our grammar rule from the beginning, drop any ones. Let's watch this crisscross method in action with aluminum oxide. First, we write aluminum, Al with a 3+ charge. Then oxygen, O with a 2- charge. Now we do the crisscross. The 3 from the aluminum crosses down to become the subscript for oxygen. The 2 from the oxygen crosses down to become the subscript for aluminum. The positive and negative signs completely disappear because at this point we are simply counting atoms, and we end up with Al2O3. The underlying logic here is just beautiful. Think about it. 2 aluminum atoms with a 3+ charge gives a total of +6. 3 oxygen atoms with a 2- charge gives a total of -6. +6 and -6, they balance out to 0 perfectly. So how do we actually speak the names of these compounds out loud? For binary ionic compounds, the rules are elegantly simple. The name of the positive cation goes first, and we don't change it at all. It stays exactly as it appears on the periodic table. But for the negative anion, we drop the normal ending of the element's name and tack on the suffix IDE. So, sodium and chlorine come together to become sodium chloride. Magnesium and iodine become magnesium iodide. It's a remarkably consistent global language that lets any scientist, anywhere, instantly know what elements are interacting. Wow, we have covered an incredible amount of ground today. You've learned how to read chemical formulas, how atoms form positive and negative ions or share electrons to reach stability, and the exact crisscross steps to name binary compounds. Chemistry is quite literally all around us, and every single molecule has a fascinating story told through its elemental bonds and specific formulas. So I leave you with this final question. Are you ready to decode the chemical world around you? Next time you're brushing your teeth or drinking from a water bottle, take a look at the ingredients and practice reading the hidden chemical grammar you've mastered today. Keep exploring, keep asking questions, and I'll see you in our next explainer.